Good afternoon to everybody. Let me first thank the organizers for this beautiful conference. I'm, of course, extremely honored to participate to this conference in honor of Deepak's Boltzmann medal. I actually, we have not collaborated, Deepak, but indeed, during the last years, I've been collaborating with many Indian colleagues and students, and through them, I could really, I think, understand, I mean, the deep influence that you have on this, on our community. And to a large extent, that's why I chose to talk today about this problem of the 1d-Coulomb gas and local statistics about this system. This actually a work that started in 2017 with Abhishek, Anupam, Satya, and Sanjib. And more recently, we made some new progress with our student together with Satya and Anna Flack. So the idea is essentially to start about a relatively old problem. And I just flashed out some famous papers on the subject. As you see, these are relatively old references, and since then, the theory of Coulomb gases, and in particular, thanks to the progress in randometric theories, this is a field which has been evolving quite rapidly during the last 10 years. And somehow I want to show you how we have revisited this old problem with new perspectives, with slightly more modern one, if I may say. So what I will talk about is essentially based on these three papers. As you can see, I mean, I will not try to, I will not dare to compete with David, but this is actually with three former PhD students of Deepak, and even Anupam can be also considered as a scientific grandson, I think, of Deepak. So this is indeed quite close. So the model is quite simple. You just consider a system of positive and negative charges, n of them. So it's a neutral one, and you have position xi for the plus, xyi for the negative ones. And this is the Hamiltonian. Okay, so you only have Coulomb interaction, and since we are in 1D, one-dimensional system, this interaction is just mod x. Okay. Now, treating the full problem is actually quite non-trivial, but what we can try to do is what people have done since a long time, is basically to treat one of the two components on a macroscopic way, say the negative charge, and write an effective Hamiltonian for the positive charge. So how to do? I mean, the basic way to do that is just to consider that these yi's, they just constitute a uniform background with a certain uniform density. So to do that, I need to look first at the model on the minus L plus L, and eventually I will look at the minus L or plus L, say, goes to infinity. And you see that this interaction term between the x and the y's, if I assume this uniform background, I can just treat it in a kind of mean field way, if you want. So I just replace this y by their uniform density. And if I do the explicit integral here over y, what you get is that, so this L square is just a constant, which will get rid out. But this guy, you see, I've now generated an effective harmonic potential. Okay, so that's the model that I wanted to start. Repulsive interaction together with this confining potential. Now, it's quite clear from the argument from the physical system that I have here that A and B are some numbers which are typically of order 1. And the first thing that I want to do is to have an estimate of the typical scale of these xi's. As we will see, because of the competition between the repulsion and the confinement, the system will be supported on a finite domain, and I want to estimate the typical scale of this domain. Let's call it Ln. And let's just rescale xi by ln, where x tilde now are just number one of order 1 terms. And the scale ln can be just estimated by balancing the confining term, which is of order ln squared times n, since I have n terms in this sum. Okay, so that's where I stopped. Okay, so if I just now recast everything in terms of this x tilde, well, I have this energy functional here. Now you see that this x tilde are just now terms of order 1. In the following, I will just forget about this x tilde term here and come back to a slightly simpler notation xi. But what I want to point out is that you see that typically each of these terms and the energy itself is now of order n cube. Okay, I have this n square term times n and the same here. So typically the energy in this model will be of order n cube, and that's the model that I want to study. Okay, so let's. So this is basically what I want to look at. I have these particles; they are now supported or in the presence of this confining potential. And the first thing that I would like to estimate is the average density. How can I compute that? Now you see that there is this term here is a bit embarrassing or complicated to treat because of this absolute value. Now the trick to get rid of that is just to look at the sectors where the particles are just ordered. Okay, this trick is not new. Actually, it was already in these original papers of old papers by Lennart and Baxter. But the nice thing is that once you have ordered the particles here, well, you can just get rid of these absolute values and you get something which looks like quite simple. And you can just even complete the square. So it's just a quadratic form here in terms of this xi. But you see that because of this double sum here of I and j, you have essentially a potential now that depends on the rank of your particle. So you have an explicit I dependence here in this potential term. Now, if you just indeed complete the square, that's what you get. Okay, so that tells you that since this again is of order n squared, if I'm looking at what happens in the large n limit, well, the positions, the equilibrium positions will be the one that minimize this quadratic form. And they are obviously quite simple. This is what is written here, okay? Now, if you look at them, well, the first obvious property is that they are equispaced. Okay, these are linear functions of I. And if you look at the leftmost one, it's close to -2 alpha. And the rightmost one, which now for n, I equal to n, is just close to +2 alpha. So basically what you get is that you have just a uniform density, which is supported between -2 alpha and +2 alpha. Very simple. Okay, so that's what you get. That's the profile that you get. So this is, by the way, quite generic property of Coulomb gases in d dimensions in the presence of a harmonic potential, but I will not comment too much on that. Now, all these things, of course, are quite well known, and what I want to discuss here are not properties which correspond to global quantities like this average density, but I want really to address more precise questions about local fluctuations in this model. So what I will discuss here, if I have time, the first thing that I will discuss are the fluctuations of the rightmost particles. What can be said about this guy? It will be very close to 2 alpha, but what are the fluctuations of it? Sure. Yeah. So indeed, so because of the long-range interaction, you have an energy which is like n cubed.
So like if alpha was 0, I would want the energy to be extensive.
Sorry?
If alpha was 0, I would want the energy to be extensive, right?
Yes, that's true.
So therefore, why don't I choose alpha such that I still have extensivity property?
Well, I mean, because you have seen, I mean, I need really to, initially, I mean, the particles, I mean, the model that I started with were just the coping constants, which are really of order 1. And that's really the physical system that I have tells me that typically I will have something which is of order n cubed. I could make what you say, but I would have something which is a slightly different model. Okay. So, yeah. So another thing that I would like to discuss is basically the spacing distribution between two consecutive particles. And if I have time, I will address the question of full counting statistics, which is the number of particles in a given domain. But I'm afraid I will not have time really to do that. So why should that? I mean, why should I be interested with this? Well, part of the motivation for this work, for this question, was actually the study of random matrices. So for those of you who have never seen it, if you look at typical random matrices like Hermitian matrices, where you put random numbers. If you look at the joint distribution of the eigenvalues, you will look at something like that. You will obtain something like that, okay? So beta will be equals to 2 if you look at Hermitian matrices, beta equals 1 for orthogonal matrices. And you see that if you re-exponentiate this term here, that's what you get. You get this log term here. So beta plays like a role of a kind of temperature, if you want. And now you have this quantity. Okay, so you have this quadratic potential. You can interpret this as a Boltzmann weight with a quadratic potential together with this logarithmic term. Now this term is sometimes called the log gas, simply because this is the Coulomb interaction in 2 dimensions, but the particles are confined in 1D. Anyway, if you look at the density in this model, it's actually slightly more complicated than what we saw before in the 1D Coulomb gas, and it has this nice Wigner semicircle form that you all know, many of you at least know. Now, what happens here if I look at the largest eigenvalue? Of course, what you expect is that the largest eigenvalue will be very close to the right edge. And this is indeed what happens in the large n limit, but then you would ask, well, okay, fine, but what are the distribution, what are the fluctuations of these eigenvalues? It turns out the distributions are actually, the range of the distribution, of the fluctuations are quite small. They are scaling like n to the power minus 2/3, and you probably know that they are given by the celebrated Tracy-Widom distribution. Okay, so if you scale the things properly, I mean, that's what it says, that in the limit when n goes to infinity, the cumulative distribution of the largest eigenvalue, lambda max, is given by this f beta function. So beta here is this index there. And this was first computed in the case of beta equals 2 for GUE by Tracy and Widom in 1994. And as you probably know, this distribution actually has since then appeared in many systems, not all of them being related to random matrix, by the way. And it has generated a lot of interest. So I will not enter too much into the details, but it's actually possible, at least for the classical values of beta equals 1, 2, 4, one can write the Tracy-Widom distribution in terms of the solution of some Pain-Levé equations, of ordinary differential equations. And this F2 has some kind of explicit form here. You don't need to remember that. That's just to show you that one can compute this explicitly. And for other values of beta, there are even more complicated construction, which are also very nice, but I will not enter too much into the details. Now, the interesting point is that this Tracy-Widom distribution turns out to be quite robust, quite universal, in the sense that if you now look at this distribution, but instead of having a lambda I square term, as I would have here, if you just take another potential, V of lambda I, then you can show that provided that V lambda is sufficiently regular, the limiting distribution of the largest eigenvalue will again be Tracy-Widom. So there is a very wide universality class. And a natural question that you may ask is what happens if you not only change the potential, but if you now change the interaction? Okay, so that's how we sort of came to this problem, where instead of looking at this log interaction, now you look at the mod lambda I minus lambda j interaction. So what happens there? Will it be still Tracy-Widom? Will it be something else? And if it's something else, can one compute it? So the answer is yes. Oops, sorry. Okay, non-log. You can have, okay, there are some models where you can have non-log. I mean, for instance, you can have log-sinh interaction, which arises from some specific matrix model. Yeah, of course. So log-sinh in some model can actually be thought of as typically a mod lambda I minus lambda j. But strictly speaking, the mod lambda I minus lambda j, as far as I know, there is no counterpart in random matrix theory. Physical systems, yes, because I mean this is really the true Coulomb interaction. Okay, so so this really the fact that we looked at this mod X. I mean there are 3 motivations. The one is to go beyond this log. The second is because physically this is this is, I mean, interesting because of that. And the third one is that it's exactly solvable. Okay, so what can we say there? Well, what we can show, first thing is, what we can show is just estimate the typical scale of the fluctuation. So again, the largest, for the rightmost position will be very close to the right edge, as you would expect. And if you want to estimate the width, well, you can just apply or use this standard argument from extreme value statistics, which says that, okay, if I want to estimate the typical scale of X max, then basically I can just get it by saying that in the interval X max to alpha, around here, I will typically have one particle. This somehow assumes that the particles are independent. We know this is wrong. But nevertheless, we also know that this kind of approximation actually works in all the models that we know, at least in RMT. If you do that, since rho is just uniform, what you get is that the width is actually of order 1/n. Okay? So you see that here in this model, you see clearly, I mean, the typical interparticle distance is also 1/n in the gap, you know, because I have n particles on an interval which is of order 1. But so that, and this is also the same scale at the edge. Okay, so you have a uniform scale everywhere, which is not very surprising since the density is just flat everywhere. Yes, please. I will come to that. Yeah. So this is something that I will discuss. Yeah.
This function is not the Tracy-Widom.
Okay. Now the question is, well, what is this function? Yes. Okay. So indeed, what we can show is that this function actually, in the large n limit, we can compute this limiting distribution. So this was done in this papers. So it converges to a function f alpha, which so depends on alpha, which is the interaction strength. And this f alpha actually is a solution of a quite non-trivial non-local differential equation, which is written here. Okay, so it's obviously the first order one, but it's non-local. Okay, so it's quite non-trivial. Now, what is the A alpha here? Well, the correct way of thinking of this is that this A alpha may be thought of as a kind of eigenvalue. So what I need to solve is really an eigenvalue problem in the following sense. F alpha here is a cumulative distribution. Okay, so it has to satisfy a certain set of boundary conditions. So when x goes to plus infinity, F alpha has to saturate to 1, and it has to go to 0 on the other side. And of course, because it's a cumulative distribution, it has to be positive. Now, if you think of this equation, if you want to solve it numerically, well, what you will do is typically you can start from x equal to plus infinity, and you will start very close to 1. And then you can solve easily this equation here. And for a given A alpha, well, typically your function will converge in minus infinity to some value, which typically will not be 0. Okay. Now, it turns out that there is a fine-tuning. And in that sense, this A alpha can be thought of as a kind of eigenvalue problem. There is a unique choice of A alpha, which allow you to tune this limit at minus infinity. And this is something that can be done relatively easily numerically. This is just a kind of shooting method. And then you can just compute this quantity. You can just plot it numerically. I will show you some plots. Now, nice interesting thing is that you can also compute its asymptotic behaviors. Okay, so you have a Gaussian behavior for the right tail, and you have a non-trivial exponential minus mod x cube to the left. So that's nice. These are plots. As expected, it works very well. Now, let's try to compare to this Tracy-Widom distribution. Okay, I mean, formally, we see that they are not the same, but let's try to be a little bit more quantitative. And let's look at the tails, for instance, which is a good way of comparing the distribution. So the tails of the Tracy-Widom distribution are given there. The right tail is this exponential minus x to the power 3/2. And on the left is also this minus mod x cube. So if you just compare to what we have here, well, you see that the left tail is somewhat similar to Tracy-Widom. So it's kind of Tracy-Widom-like for the left tail, but the right tail is actually quite different. Okay, so it's clear that the distributions are different. Yeah.
Sorry, totally missed the point.
Yeah. Yeah, but they are ordered. I mean, they are. Yeah. So that actually creates non-trivial correlations between them. Short range one, but that you will see how it comes. But so these are Gaussians, but they are ordered. So in each sector, I mean, I have in each Weyl chamber, if you want, they are independent, but that creates some non-trivial behavior. Okay, so this was about the typical fluctuation. Okay, so it's a bit like the Tracy-Widom distribution. Well, you can also ask what happens if I look at the large deviation. Okay, so for instance, what's the probability that the rightmost particle is just at 0, for instance, if half of the particle are on the negative axis? This is, of course, a very rare event, but the probability for such an event is non-zero. How can one get it? Well, this can be done by using Coulomb gas method. I just flashed the result here. So this is the central part, which we have already seen before. This is this non-trivial function when you are in the center. Now, if you are to the left of it, so if you really are in that region, well, this distribution is actually exponential minus n cube times some function. But on the right-hand side, well, of course, this is a cumulative probability, so it's essentially 1. But the correction is actually exponential minus n squared phi plus. Okay? So one may wonder why we have this n cube on that side, this n squared on the other side. Well, this is quite now, I mean, this is relatively a classical argument now. If I look at what happens on that side, well, if I really want to, I will not enter into the details, but I just show a typical configuration that contributes to the fact where the rightmost particle is much to the left of plus 2 alpha. What happens is that what you can show is that there is a uniform profile here, and plus here just a delta function at the wall. Okay, so that's quite particular to the Coulomb interaction. And so what you see, what you have to do is really to push this gas, and basically this has a cost, I mean, which is proportional to the energy that you need to push this gas. We know that the energy we have seen scales like n cube, and that's what you get here. Okay, so this n cube phi minus is really the energy that you need to push this guy. Now, on the other hand, if you look at what happens, what are the typical configurations that generate a rightmost particle which is far to the right? Well, in this case, what you will have to do is just to leave the whole density just unchanged. The n-1 particle will essentially sit at their equilibrium position, but only one of them will get out of this C here. And that will produce this n square behavior instead of n cube. Okay? So this is a scenario which is rather similar to what happens in this kind of models. Now you can compute explicitly this distribution. Phi plus is just simply this simple guy here, quadratic form. Now on the other side, the left tail, the phi minus, so it is a bit more complicated. I mean, so it has this simple cubic term, but you see that at some point, if you really push too far, that means if you push to the left of minus 2 alpha, well, you will have a single delta function. Okay, so we have all your particles in a single delta function, and that creates an additional transition at this minus 2 alpha, and there you can compute that there is another behavior. Now, this cubic term here is interesting because I can interpret this cumulative distribution as a kind of partition function. And this cubic term here indicates that there is actually a third order phase transition at W is equal to alpha. Okay, in which sense? Well, in the sense that was discussed in this review with Satya, but if you plot this quantity, so that's a kind of free energy if you want, and if you plot it as a function, so you minus log of Qn divided by n cube, and if you plot it as a function of W by alpha, well, you see that if I am on that side here, well, this ratio is just 0 strictly. But on the other hand, if I am on that side, well, I have something which is non-zero there. So this is this phi minus function. And because I have a cubic behavior, that means that the third derivative of the free energy will be discontinuous at this value here. and that's the signature of a third order phase transition. Okay, so that's relatively similar to what happens for other model. Okay, so other model means this kind of classical random matrix model. So let's see a very quick sketch of the derivation of this form, of this result. So I want to compute this probability cumulative distribution. Well, what I need to compute is really this partition function, but which is restricted to the fact that all the particles are to the left of W. So all the integrals here are just bounded by W. So in principle, okay, this is what I need to do. Now again, let me order the positions as I did before, following this trick by Lennart and Baxter. And what I have indeed, as Kieron mentioned, indeed, I have now a collection of Gaussians. So this is exactly what I have here. So after some manipulation, which are quite trivial, I just change a variable. Now what you have is that, so the weight itself is just a product of independent Gaussians, but you see you have now a non-trivial order that has emerged. Okay, so it's not completely obvious how to compute that, but nevertheless one can make progress in analyzing the large n limit. If you look at this guy, you see that you can write a recurrence equation if you start to take the derivative with respect to x. I mean, it has this structure that we like. And so basically, if you take a derivative of this function here, so this is exact for any n, and if you take a derivative, well, that's the recursion relation that you get. Okay. So now you can, if you say now, okay, what happens to this relation in the large n limit? Well, you assume that this one will go to some scaling function f alpha independent of n. Now, what should I do with that? Well, if I look at d alpha, you see that, so d alpha infinite means that now I integrate from minus infinity to plus infinity. So the model that I have is a model of short-range interacting particles. So it's clear that computing explicitly the partition function is obviously quite, I mean, is non-trivial, but nevertheless, I can safely say that since it's a short-range interacting particle system, well, the free energy will be extensive, and that's all what I need, because you see that now that what it means is that this guy is just a of alpha to the power minus n. So log of a alpha is just the partition function per particle in this model, and then this is the a alpha that I had before. So I don't know it, but I can now compute it as I explained before. So that's how you get it. Okay, so if you take the large n limit, that's what you say. Turns out that Baxter had a paper where he did a similar analysis, and he encountered also a similar function in this case. So that's for the largest eigenvalue. Okay, let's see if we can say more. So let's ask for now. So we know something about this guy. Now let's look at the gap statistics. Yeah. So one thing that I forgot to say is that you should now really remember that this f alpha, I mean, is really the hero of this talk. I mean, because essentially in this model you can compute whatever you want in terms of this function f alpha, basically. So let's see how it works. Now, if you look at this guy here, again, the typical gap at the edge is of order 1 over n, and this is, we already discussed the typical spacing between two particles. Now, the question is whether I can compute this h of alpha. Well, this h of alpha, indeed, I can get it. So it's a slightly more complicated expression, but again, it's an integral that involves this f alpha again that we have seen before. So it starts to be a bit involved. But nevertheless, we can estimate and take lots of asymptotic analysis. So here's what happens. So this is a plot of this function as a function of z. Okay, so there are two things that I want to notice is that indeed, so first, I mean, this answered what Laetitia was asking. In the case of random matrices, it is well known that if you look at the same question in the bulk, say, what you know is that you will get something which is called the Wigner surmise. And because of this term here, the probability to have two levels which are extremely close to each other actually vanishes. Now, obviously, here this is not the case. So that's pretty different from what happens there. And on the other hand, it has the Gaussian tail, but the Gaussian tail is easy to understand because it's basically the same tail as the distribution of the rightmost particle. If you want to create a big gap here, what you will send, you will take this guy very far away. So that's roughly the argument. So fine, this is what happens at the edge. But what about the behavior in the bulk? Okay, one may expect that the distribution in the gap. Okay, I will just skip that. What happens in the bulk? Okay, so now if I look at really what happens, so this is something that we did recently with Anna, our PhD student. Now, let's assume that, let's look at what really happened close to the center. Okay. Well, close to the center, you see so let me call GI the ith gap. So this is the first gap, the second gap, this is the ith gap. Well, because if I really am in the gap, that means if I here is over the n, okay, so let me scale I with Cn, this is what I call the bulk, then clearly the density being uniform, the distribution will not depend on I. Okay, and in particular, it's easy to compute the mean value. The mean value will be just 4 alpha divided by n, obviously. So what about the distribution of that guy? Well, it's again, it assumes again this kind of scaling form. It has also some large deviation form that I will not discuss. But what about the typical one? Well, the typical one now as a product now of this F alpha, you can somehow understand where this product comes from. It's just because you need to have basically, you will cut your system in two halves. And on these two halves, basically, you will have particles which are constrained to stay on a half semi-axis. And that will, you can rewrite them in terms of the distribution of the rightmost particle, rightmost or leftmost particle. And that's why you get these two F alpha with two different signs. It's fairly explicit. And again, you can analyze asymptotic behaviors, you can plot it, and that's what you get. So it has a quite interesting behavior. So first, you see that now it has this bell shape, and it has a maximum at 4 here. 4 is just the mean value of these gaps, so nothing really surprising. If you look at what happens close to 0, well, it's not exactly 0, but it's very strongly suppressed. So you see, I mean, it's very small. Here it's on the log scale. And more surprising, so this is first thing which is slightly different from that. More surprisingly, I mean, you have this exponential minus z cubed term. Okay, so if I were talking about that here, we know that we would have a Gaussian tail here for Hermitian matrices or for this kind of guy. Here we have a non-trivial exponential minus z cubed. So you see, I mean, if you just look at what happened at the edge on the one hand, what happened in the bulk on the other hand, well, you see that the behaviors are quite different, and that's okay. One of the nice pictorial result or message to take from that. Again, everything is governed by this magic function f alpha. Yes. Yeah. So here it actually it doesn't go to 0. It goes to a constant. Okay, I think it's quadratic. But okay, I haven't. I forgot actually the behavior of it. In principle, one can analyze it in detail. I don't think we have done that in detail. For what is sure is that you have a finite value here, and although it looks small, it's non-zero. Okay, so there is a very strong suppression. Okay, so I was just about to conclude. Well, the first thing that so I tried again to have a sort of more modern view on this whole problem, and in particular inspired by what we have been doing on random matrices. The first thing is that if you look at the largest eigenvalue, or the rightmost particle in this context, well, you obtain something which is not given by Tracy-Widom, but instead by this non-trivial function that I've shown. We could get the gap statistics both in the bulk and at the edge. And interestingly, this is actually not given by the Wigner surmise, and that's actually in good agreement with the recent work by our friends for the more general risk gas, mainly based on numerical simulations, where it seems that generically this Wigner surmise that doesn't hold. Doesn't hold means that in this case, what I want to say even something a bit more precise, is that you probably know that the Wigner surmise actually was obtained by solving the problem for n equals 2, and that's what produced the famous Wigner surmise. If you do the same here, if you do the n equals 2, well, you will get a Gaussian tail, which obviously is not correct because we have this exponential minus z cube. Obviously, it would be quite interesting to interpolate between the bulk and the edge. It's actually not so trivial for some reason. I didn't have time to discuss the full counting statistics, but we can actually compute this explicitly. I just flashed this buzz name, strong hyperuniformity, which just means that the system, as you have seen, is extremely rigid, and the fluctuations, so the variance typically turns out to be of order 1, both in N and in L. And okay, we have more explicit results in the papers that I mentioned. And with that, I will thank you for your attention.
Any questions? Yes, Herbert. Thank you very much. I mean, very interesting. I mean, so I missed sort of one issue. So you have this, absolute value potential. I mean, between if I start to change, I mean, let's see, I keep the confining x squared, but I change that potential. I mean, the phenomena which you described, I mean, do they depend on the fact that, you have this absolute value at small x, or does it depend on the full function, or could I change, could that repulsion sort of increase in a different way? I mean, that's sort of.
Yeah, so that's not completely clear. My intuition is that, yeah, I mean, in these cases, probably, I mean, okay, in the case of the log gas, for instance, it has even been proved in some cases that if you have a logarithmic singularity at short distance, then you will obtain this. So it's clear that here, what matters is really what happens on larger scale, I guess. We have also, similar studies can be done for the risk gas, no, with this 1 over xi minus xj, and there you also see, I mean, in general, it's quite complicated to get the typical fluctuations, but you can obtain the large deviation functions, and they clearly indicate that this will not be Tracy-Widom either.
So is there a simple pushing argument to see the Z cubed behavior at the right edge? Because you're basically pushing all the rest of them.
Yeah. So in fact, if you combine this argument with the scaling, so if you say that the gap, for instance, and the gap has to be of order 1 over n, so that means that you expect a function of gn, and now you say, I also know that to push or to create this gap, I will need an energy with exponential minus n cube. Then by scaling argument, then you get this g cube. Yes.
And how does it look just in the second, third gap from the edge? Like,
yeah.
Is there a way? I mean, you said it's non-trivial to scale.
Yeah. Okay. So I guess the second gap probably can be done explicitly. Well, for that, you really need to compute this d alpha. I mean, this but for finite n. I mean, this partition function. So it will depend on I in a non-trivial way.
But numerically, you've seen some.
We haven't really looked at it, but it's clear that it will depend. I mean, you can see that it should depend on it, but numerically, I don't know. I mean, for instance, how you will cross over from this Gaussian tail to the cubic tail is something which I don't know how to do. It's not so easy, I think, to describe this full crossover.
Very nice, thanks.
Yeah, hello. I'm coming to your conclusion, actually.
Yes.
I will not expect, actually, looking at your model, the one you started with, I will not expect Tracy-Widom distribution, because Tracy-Widom distribution was like you had the level repulsion of particular type, and that's what it was dependent. Second thing is, you are saying that in the bulk, the distribution is not given by Wigner surmise. Again, Wigner surmise was dependent on 2x2 matrices, random matrix theory. So I will not expect to Wigner surmise anyway. And even in random matrix theory, bulk and edge, there is no, I mean, bulk differs very much from the edge. And if I'm correct, actually, I'm not very 100%, don't remember exactly. Shoshnikov has worked out actually in random matrix theory context that the edge distribution is Poisson type. And your distribution, if you really study the spacing distribution, nearest neighbor spacing distribution in the edge, it should turn out, even in the bulk, should turn out the Poisson statistics.
No, this is not true. But okay, I mean, I cannot answer maybe to all the questions, but maybe the one, so again, what I meant by this, sorry, by the Wigner surmise in this case is that what I was saying is that if in this case, you compute the gap distribution for n equals 2, then you obtain a result which is really off. That's what I meant. Of course, I do not expect this. Now about Tracy-Widom, well, of course, I mean, you're right, but on the other hand, you see that there are some features which look similar. For instance, there is this exponential minus mod x cube. This is more, I think, the point which is more sort of surprising is that you see that there are still some features which look similar.
I am quite sure that you will get in n goes to infinity limit very close to Poisson result statistically.
This is n goes to infinity, so it's not Poisson, you see. I mean, it's not that it looks. I mean, it's a result. I mean, it's an exact analytical formula. So. Yeah.
Okay. Manas, let's go to the.
Yeah. Sorry. So it's really interesting that you have e to the minus s cube, and Wigner surmise analog completely gets it wrong, actually, right? So, but I'm just interested in if suppose in the smallest limit I just do n equal to 2 analog of Wigner surmise, I will, does it disagree even in the smallest limit, or?
Okay, I guess so, but I don't know how far it's different. I guess it will produce something finite. I mean, I'm sure it will produce something finite.
Right, but even the n equal to 2 will produce something finite.
Yeah.
So I was wondering.
You don't, okay, here you see, I mean, this measure is really 0 when lambda I equal lambda j.
Right, but if I do this for the Coulomb gas, then I will presumably get e to the minus s square.
Yeah, exactly.
Like
yeah, exactly. That's
and so minus s square is completely wrong because you get s cube.
But it does produce. I mean, but it's a constant value for s equal to 0, which will not be correct, of course. But yeah, but that will be more reasonable. So this is more a problem with the large s behavior.
Large, I see. Thanks.
More questions? Let's thank Gregory for a beautiful seminar.